All right, let's get right into it. If you've ever found yourself just staring at an AP Statistics free response question, wondering how in the world a grader actually turns that into a score, well, you are in exactly the right place. We're going to pull back the curtain and demystify one of the most challenging parts of the entire exam. So, take a look at this. This is the real deal, straight from the College Board. I mean, it is dense, it's packed with technical jargon, and, let's be honest, it is kind of intimidating. This right here is the official language that stands between you and a perfect score. And that's the big question, isn't it? How do we take that mess of words and translate it into clear, simple steps that you can actually use? Well, that is exactly what we are going to do right now. So, what's the secret? How do we crack this code? It starts by realizing that every single one of these inference questions isn't one giant, scary problem. Nope. It's actually graded in 3 completely separate parts, which means we can attack it as 3 smaller, much more manageable tasks. Think of this as the grader's secret playbook. Section 1 is just the setup. Section 2 is where you do the detective work and gather the evidence. And Section 3, that's where you make your case. If you can master these 3 sections, you've mastered the whole question. So, let's start at the very beginning with Section 1. All right, first up, Section 1. This is all about laying the proper groundwork. It's where you tell the grader, hey, here's what I'm testing and here's the tool I'm going to use to test it. And at the absolute heart of any test are the 2 competing hypotheses. You've got the null hypothesis, or H0, which is basically the boring, nothing interesting is happening assumption. Then you have the alternative, HA, and that's the exciting new idea, the claim we're actually looking for evidence to support. So how do you lock in full credit here? What the graders call an essentially correct? It's really just a 3-point checklist. 1, name the right test. 2, state your null and alternative hypotheses with the right symbols. And 3, and listen, this is so important, provide context. Define what your symbols mean in the story of the problem. That last part is the difference maker, because it shows you actually understand what's going on. Okay, once you've set the stage in Section 1, it's time to gather your evidence in Section 2. Now, I know what you're thinking, calculations, math, but don't think of it as just scary formulas. Think of it more like you're a detective and you're about to find the crucial clue. So yeah, you'll start by checking your conditions to make sure your test is valid, and then you'll plug your numbers into a formula. And all of that work, all those numbers, they all boil down to one single incredibly powerful value. And for our example problem, here it is, a p-value of about 0.359. But what on earth does that number actually mean? This is, without a doubt, one of the most misunderstood ideas in all of statistics. Okay, so that 0.359, it's a probability. It's the answer to this very specific question. If the null hypothesis were true, if there really was no difference between the groups, what's the chance we'd get a result like the one we got, just from random luck? Here's a really simple way to think about it. A tiny p-value means your data is super surprising, which makes you think, maybe that null hypothesis isn't true after all. Our p-value, though, 0.359. That means there's about a 36% chance of seeing what we saw just by luck. That's not very surprising at all, right? So, we've got our evidence, that p-value. Now it's time for Section 3, the grand finale. This is where we make our closing argument and translate that number into a clear, convincing, and high-scoring conclusion. And the rule here could not be simpler. You just compare your p-value to a cutoff point called a significance level, which is almost always 0.05. And the saying goes, if the p-value is low, the null must go. Well, our p-value is high, so the null gets to fly. We fail to reject it. Now listen up, because the exact words you use here are a huge deal. You never, ever, ever say you accept the null hypothesis, or that you proved anything. Why not? Because we're only looking at a sample. We can't be 100% certain about the whole population. Instead, you have to use this careful, wishy-washy language like, we failed to reject, or we do not have convincing evidence. It shows the grader you get the big idea here. We're dealing in uncertainty. But remember that careful language we just talked about? We use it for a very good reason. We have to acknowledge that even when we do everything right, our conclusion might still be wrong. It can happen. And statisticians have names for these potential mistakes. They're called errors. And there are 2 main types. A type 1 error is basically a false alarm. Think of a smoke detector going off when you just burned some toast.
You rejected the null, you sounded the alarm, but you shouldn't have. A type 2 error is the opposite. It's a missed detection. Now there is a fire, but your alarm stays silent. You missed an effect that was really there. The absolute best way to keep these straight is the courtroom analogy. In a trial, the null hypothesis is that the defendant is innocent until proven guilty. So a type 1 error, that's convicting an innocent person, a horrible false alarm. A type 2 error, that's when a guilty person goes free, a misdetection of their guilt. So, when you pull all of this together, you start to see something really cool. Cracking the AP Stats exam isn't just about memorizing formulas, it's about learning how to think and communicate like a real statistician. So here it is. Think of this as your new secret weapon, your checklist for any inference problem you face. You state your hypotheses, you get your p-value, you compare it, you write your careful conclusion, and you think about the possible errors. It's a structured approach for a structured question. And if you remember just one thing from all of this, let it be this idea right here. This whole process gives us a powerful way to look at evidence in a world that is filled with uncertainty. We're not looking for absolute 100% proof. We're weighing the evidence and making the best decision we can. And I'll leave you with a final thought to chew on. Think about a medical test. Which error do you think is worse? A type 1 error, a false alarm that tells a healthy person they might be sick, or a type 2 error, a misdetection that tells a sick person they're perfectly healthy? The right answer? Well, it depends entirely on the situation. And that right there is the heart of statistical thinking.